Embeddings and Vector Database. Hello, everyone. Today, I'd like to walk through embeddings and vector databases in system design. Embeddings and vector databases are the foundation of semantic search, RAG systems, recommendations, clustering, and many modern AI applications. The core idea is simple. Text becomes an embedding vector, then the system performs similarity search. Instead of searching only by exact keywords, embeddings allow us to search by meaning. Now, let's start with the core framework. When I think about embeddings and vector databases, I usually break it down into 5 parts. First, what embeddings are. Second, how similarity search works. Third, what a vector database stores. Fourth, how indexing and query pipelines work. And finally, scaling challenges and trade-offs. The main trade-off is accuracy versus latency versus cost versus freshness. What are embeddings? An embedding is a numerical vector representation of text. For example, the phrase refund policy can be converted into a list of numbers. The important idea is this: semantically similar text should have similar vectors. For example, refund policy and return money rules do not use the exact same words, but they have similar meaning, so their vectors should be close to each other in embedding space. This is why embeddings are powerful. They let us retrieve documents based on meaning, not just keyword matching. Embeddings are used in semantic search, RAG systems, recommendations, clustering, and classification. The key idea is this: embeddings turn meaning into numbers. Once text becomes vectors, we can compare vectors. The goal of similarity search is to find the nearest vectors to a query vector. For example, a user may ask, "How do I refund an order?" The system converts the query into an embedding. Then it searches the vector database. Finally, it returns the top K similar chunks. Common similarity metrics include cosine similarity, dot product, and Euclidean distance. For text embeddings, cosine similarity is commonly used because it compares the direction of vectors, which works well for semantic meaning. So if two pieces of text have similar meaning, their vectors point in a similar direction. The key idea is this: vector search finds meaning-based nearest neighbors. What is a vector database? A vector database is a database optimized for storing and searching vectors. It usually stores 3 things: the embedding vector, the original text chunk, and metadata. For example, one record may contain an embedding. The text, "Refunds are processed within 5 days," and metadata such as document ID, section, and source. The metadata is very important. It allows filtering by source, region, document type, timestamp, permission, or business domain. For example, we may only want to retrieve documents from the Help Center or only documents available to a specific user. So, a vector database is not just a place to store vectors. It supports fast similarity search, metadata filtering, scalable indexing, and high-throughput queries. The key idea is this: a vector database makes semantic search fast and scalable. Now let's talk about indexing and the query pipeline. A simple linear scan over all vectors is too slow at scale. If we have millions or billions of vectors, comparing the query against every vector is expensive. So vector databases use indexing. The simplest index is a flat index. It gives exact results, but it is slow at large scale. Production systems usually use approximate nearest neighbor search, or ANN. Common index types include HNSW and IVF. HNSW is graph-based and commonly used because it gives a good balance between speed and recall. At query time, the pipeline usually looks like this. The user sends a query. The system converts the query into an embedding. Then it searches the vector database. Then it applies metadata filters. Then it retrieves the top K results. Optionally, it re-ranks the results. Finally, it returns the results. In many real systems, vector search is also combined with keyword search. This is called hybrid search. Semantic search is good for meaning. Keyword search is good for exact terms like IDs, error codes, product names, and policy names. The key idea is this: indexing makes vector search fast, and hybrid search improves retrieval quality. One important design detail is chunking. Documents are usually too large to embed directly. So we split them into chunks, usually around 200 to 500 tokens. Chunking has a trade-off. Small chunks give more precise retrieval, but may lose context. Large chunks preserve more context, but may introduce noise and increase token cost. After retrieval, we may also use re-ranking. For example, the system may retrieve the top 50 results, re-rank them, and then keep the top 5 final results. Re-ranking improves precision before sending results to the LLM. The key idea is this: chunking controls retrieval granularity, and re-ranking improves precision. At scale, embedding systems face several challenges. There may be millions or billions of vectors. Queries may have high QPS. Embeddings may consume large storage. Documents may update frequently. And re-ranking can add latency and cost. Common optimizations include sharding, caching, approximate search, batch embedding, vector compression, limiting top K, and using metadata filters. Freshness is another important trade-off. Batch updates are cheaper, but less fresh. Streaming updates are fresher, but more expensive and complex. So the main trade-offs are accuracy versus latency, recall versus precision, cost versus quality, and freshness versus efficiency. To summarize, embeddings convert text into vectors that capture semantic meaning. Vector databases store those vectors and make similarity search fast. Together, they enable semantic search, RAG, recommendations, clustering, and many AI systems. The final insight is this: embeddings turn meaning into vector distance. Vector databases find nearest neighbors in that high-dimensional space. Thank you.